Hi everyone. Today I will give a talk of this paper based in visual potential separation with the threshold Gaussian precise. I want to talk about this paper. The two reasons. Firstly, I feel like how it simulates the Blanchard separation precise is kind of different to our traditional IC algorithms. It's kind of doing more like a modeling of how the lattice sources look like. And also all their assumptions and their thoughts kind of very interesting. And another thing is I'm always looking for a Bayesian statistic validity method. And, and for this paper, this presentation create this related paper. So just stop me anytime if my explain confuse me because it may be better for both of us to understand it. The content I will include, I firstly talk about the background of how this paper, why they think of new algorithms, and also how it's related to the current IC applications. And the paper mainly on the neural imaging level separation. So it's still based on that. And then I will go through the setup of this algorithm and how what they assume and why these assumptions mattered. And actually, these are the most interesting part of this paper. And then I will go through posterior computation of how they settle them to decide the final posterior and give some experiment result and some future work to plug into this. First of all, I would talk about the background. The existing ICA model, independent component analysis model, typically assumes the component's spatial sources signals cross brain as independent random samples from a distribution. So what it means that from Flores, it said that for the random source of ICA result follows some follows the random samples from distributions, which means that the result of IC algorithm do not consider about spatial independence. Like in our lab, we use informatics a lot for the IC problem. So we know that it has some IC algorithm, informatics or fast IC, they have a objective or contrast to optimize the result and finally get some components. It will have some features, but we do not have at least through the algorithm itself, it does not have a strong explanation of why this components matters. And this paper will through a different way. They will try to estimate the random source by giving an assumption how the random functions should look like. And the second, the raw results from existing IC methods are often noisy and require thresholding to identify significant source signals in the brain. So the problem is after we're running the IC algorithm, we get components and we need, because my data is very noisy, we need to settle down a threshold to select the active regions. But there comes a problem is when given different data from a different research project, we do not have a reasonable comparison between these different works. So because the selecting threshold will still based on different methods, engineering, biology and stuff. So it's hard for comparison problems. And the biggest challenge for the informatics is deciding how many of the 11 sources. So from my personal knowledge, I remember many years ago for our informatics, we tried like at the beginning for the resting state, we decided like around 20 to 30 components, and gradually increased to like for kernel number have 53 components. And recently, I've heard that there are over 70 components. So everything is still based on a lot of engineering or biological works to decide which components matters. Because informatics, it will directly working on reduced dimension data. So deciding number of levels is a challenge. It's not something Informatics can solve. But this paper in the basic methods can decide how many latent by some their computation tricks. So the main contribution of this paper, firstly, is using TJB's thresholding Gaussian precise, which can, so they assume the latent sources of the MRI are sampled from Gaussian precise, and for to make sure the sparsity, because based on a lot of research, our brain regions for the active neural networks in the brain is will like concentrate to a specific region. So, so the latent components will theoretically consider as sparse, and it does have spatial dependence, like the voxels between voxels and nearbys are related to each other. So, but for traditional IC algorithms, they do not consider or assume these things. But this method, it will consider by using the TJB, will consider these features. And also, they do not need to thresholding after separation. Separation is because it will have the thresholding is also a trainable or learnable parameter during their sample process, and then it can estimate the number of latent sources. That's a main contribution of this paper thing. Now, let's start with the algorithm. So, still as the latent source separation, the model basic framework is consider our observation X is like I the number of subjects and V the number of again the voxels or brain region. So it's a linear mixture of some latent sources Sj. B is represent brain. The brain BV is a small region or voxel of it. So AIG is one element of the mixing matrix. So it's a summation of so one observation of the brain image X is a linear mixture of a couple of latent sources S, the capital Sj. So we assume there are a total of two latent sources, and sigma here is a noise. And in this paper, this noise is also a learnable parameter. So this is how they settle down this model, and a couple of notations to definitions to understand. So the capital Sg represent the intensity of a domain, and for the real sampling process, the real level model is Sg to C. Sg to C represent the location in our brain. As it's not the voxel in this condition, because it's just like one point of that part. And the intensity of that region can be represented as a derivative of that part, and M is the Lebesgue measurement for 1D, 2D, 3D is the length, area, and volume. So this will represent the intensity of this domain of part. So the capital and small sg will represent different things. And one thing is how they define the effective number of forces. I represent an indicator, function. Sg, the L1 norm represent the absolute value of the function. Sg, the J is 11 function. So it should be larger than 0 to activate. This is just a basic definition. During their training, their optimizing, it will have other tricks to settle down this. So basically, to define the effective number of sources based on as long as the sampled latent sources is not just a 0 through the brain domain, it will be considered as an effective forces. So this is what this equation is trying to say. And for parameter space, I'm firstly going to subject because it's easier understanding. For mixing matrix, the jth column of the true mixing matrix A star belongs to a space A, G, and belongs to the n space real numbers. So all of so basically, you can read the assumption, but basically it's trying to say that because it cannot just limit um, the scale of the Latin forces, they're trying to uh, control the yes, trying to control the norm of the mixing matrix for each column represent the linear yes represent the weight of each of the 11 sources, and it will be settled down the norm of square n. So it's just for control of the scale and for a better simulation. So that the mixing matrix can be sampled from specific distribution like the one Mrs. Fisher distribution. And for assumption one, so I summarized it in I think either understand part. It's already very clear in the assumption one if you want to read it, but all they're trying to see is for all the 11 sources, for each of the active region, they do not have overlap. And for each of the 11 component is a sparsity, which means that has only for each of the 11 sources has only one active region. Yes, and for then another to assume for Rj represent an active region and for the J, oh, not just one active region. So represent the J's active region. See how this. Uh, yes, for all of the active regions, they do not have overlap, and for each of the latent forces, latent functions Sj, it will be active into that regions, and anything outside of the regions will be marked as zero. This can be defined for the function sparsity. And also during their sampling precise will follow a threshold. So only values above the threshold will be considered active. So even if inside this region is below the threshold, is still considered as zero. And another thing is it will define smoothness in the active regions of the Latin sources. Because so what they do is define is on a row zero order derivative. So which to make sure it's smooth enough, because it will the Latin functions will be sampled from Gaussian precise. So if you want to sample it, it's very high dimension. To sample it, you need a much smoother uh, smoother functions because it will doing like an eigen decomposition so that it can be for easier representation of the Latin functions. I will explain this part later for the compulsory part. Uh, is anyone has confusing of this part? I think it's kind of
it is. I'm more interested to get to the actual method. This is
so for assumption three is trying. So what they did is this part is they are trying to concentrate the active region uh, to to be not too large or too small. They give some. I wasn't found how they define these values, but as a reasonable like this, if considered 2D, the active region should be it being scaled under some ratio with the real measurement of the brain. But so for all the assumptions, it's just not to make the active region not too large or too small. So for mathematical explanation, I don't have a very strong explanation of it. If you want to read it now, or I continue. So for their proposition, and based on all of these assumptions, and there for the all assumption, I think you do not need to read it because it's trying to use a fully mathematical representative. All they do is trying to explain identifiabilities like the sign flipping for the ISA problem with like they do not care about positive and negative. They consider the same results as most ISA do. And there are full improvement of this part in their supplemental material. So I will not go through that. If you're interested, you can go check it. It's based on it's trying to use uh, okay, I will not explain it to confuse others.
So it's different identifiability than linear ICA?
No, the same. This is
It's the same.
What?
I think at least up to this point, we're like the assumptions in this proposition are all the stuff we talked about in the last year.
Yeah, it's the same. The same. It's a sign flip, it's a positive and negative.
Yeah.
They have proved they're interested to the supplementary material from the couple pages.
I have a question. It must be related by this like if you flip the sign of the whole thing or only some components.
For some components, or whole things, so it can be any combination. And then how their price specification. First, as I mentioned, for the mixing matrix, they have this concentrated norm of each of the column to be square root of n. So, which is very matched with the Bayesian spatial distribution, which is defined on our hyper-unit sphere. So, the prior of the mixing matrix will be defined on this Bayesian spatial. So as I remember, for the heat of their experiment is set to 0, and this way, for this sampling, the price sampling can be sure that A is the scale fixed, and for the Latin functions, the price settled to be a thresholding Gaussian precise. Still, as I explained for the assumption 1 is for sparsity assumption and the spatial relations. So for to see, you could see the point one location in the brain, and the BJ here you should not confuse with the domain of brain. The B here is represent Gaussian precise. So it's a represent the J's Latin functions, and for the small g with the theta, right? So it will be settled above the threshold of the Gaussian sampling to be settled as active because Sg is considered as a sparse function.
So is it just the regular Gaussian process defined everywhere plus the threshold function looks like from the information?
You mean
I scanned through this paper, didn't read it super carefully, but I'm curious, like the ability to discover the number of latent dimension and to do the automated thresholding. Like the automated thresholding, I was getting a reason why we couldn't incorporate that to a linear ICA as well.
Yeah.
And even number of you just can put a sparsity constraint.
Right.
The way they do it, right? If a source is 0, then it doesn't exist.
Right.
So that is too strict. They have a probability to decide how many actives of box sources, not just about 0. And the thing is how they define the probability. Like if they do 1,000 samples, like there are 5,000 now activated, so we consider it as active. So there is the land sort all the way down is not less than 500 we consider it. So this is how they consider how many active methods. So the trick is how you select the ratio. So they cited another paper say, this is a common accepted ratio and we use it. That's why I think, okay, yeah, you said.
Yeah, what I'm more curious about ultimately this paper is why the Gaussian process and the specific choice of prior might give them more reliable results than linear ICA, because their results are convincing, which you haven't touched on yet. But
well, actually, there's some which shocked me. I really want to give up this paper. Very quick. Because when I read up their supplementary material, we will run Informax first. And this, using their mixing matrix and at the initial value. So I think, okay, so it's already considered all this. Maybe it's because if you directly working on a mixer, the computation will huge.
Yeah.
And it's already slow based on that.
That's an unfair comparison here as well. Okay.
And for another two prior specification for the sigma, the noise is considered as the inverse gamma is for conjugate prior. And zeta. And zeta is considered as a non-informative prior, which is just as long as it's positive, it will so consider as a positive number for the thresholding where this is threshold. Remember, there's a threshold of the Gaussian precise. Okay, so their base inference. Okay, for I need to if anyone is confused from the prior design. Okay. So for the base inference, how they decide the final mixing matrix. So they are trying to use the Monte Carlo Markov chain, like like if you have 8 of the samples of the pairs, a mixing matrix and 11 forces. So the mixing matrix will consider the average of all of the samples. And for detecting the active regions, so they need first compute the the posterior inclusion probability of for each of the location. So it will still, as I mentioned, consider as long as probability of the latent functions is not zero, is zero or not at the location. So because there are a total of 8 samples, it will compute the ratio of it and to detect the PID result. And so the active, so the latent functions will be considered as this. So this is just the average. You don't need to worry about it. Average, and this is the summation of all of the non-zero values and to average of that. So this how you consider SG. And elsewhere, if it's not, it will be zero. So to decide active region, they're using the effective number of sources as like this one. So if it's active or not.
We want probability, right?
Yes, we want probability.
Because this indicator function is indicator function. It's binary.
Yes. And yes, this is how. And by averaging and for the ratios above the 0.5, like their total eight samples.
So PIPJ is posterior probability of J, right? And the total is just the sum over J, right? For the joint probability.
Over samples.
No, the joint probability would be, it's whether J's component or ith component, right? It's the NOR, not.
No, what they're doing is trying to say if this location active or
So my expert of the Greek naming is Pavel. Is it the psi or what is that letter? The PIP of
Kasi.
yes.
Yes.
Yeah, I
Oh,
took
G.
note here. It's Kasi.
Yeah. Oh, is it chi? No, that's not the little chi. So Pavel, do you know detect trait PIP of what? How do I read it aloud? What is that?
I can find it, which one.
I forgot. Yeah, I mean
Yeah,
this one. Yeah.
Yeah.
Chi.
but it's written exact, but I don't know how to pronounce it.
Psi.
See, but
How does it
Yeah.
try or she?
I think
Either the capital is chi.
oh, no, it's with X.
Yeah. So the capital letter, but well, then it's chi. That's how it's pronounced in English.
So I think it's psi.
It's written, but it's pronounced chi. It's like the chi-square criterion is
Yeah, chi is a different letter.
is it different? Okay. Well, let's go with psi. So PIP of J of psi, PIP of like so then PIP of I of psi will be different, and their total combination will be one, right? Psi has to belong to. It's a convex combination. It has to belong to some uh, component.
No, they're not.
What do you mean? J is the component, right?
They're like here, J. Yeah, there's a SJ, the Latin, the
Yeah.
J is Latin source, and
There's
the
probability of
SJ is sampled from a Gaussian precise. So they're like an edge of them.
well, but you are saying that probably there is a definition POP of J. Okay, let me see. You're saying this is that, but this is probability of this voxel belonging to that
No,
component.
The whole part is a probability, and this one is function.
Yeah, yeah. Does it belong to this component or not? This function is an indicator function.
No, SJ is not indicator of itself. Oh,
Does it belong to SJ component?
not indicator. It's the sample for one of the from H. Is like S small h. It's one sample from the Gaussian precise. It's a function. It's not an indicator function.
Mhm. So it doesn't have to be sparse. It's a continuous function,
Yes.
but it can be equal to zero. So we're just checking whether it's not equal to zero. What did I P again? PIP. You looked it up.
Posterior inclusion probability. I think it's kind of like marginal posterior.
Okay. Let's go.
It's marginal. What are they marginalizing out?
Like they have a couple of parameters because they use the deep sampling, so it's the marginal of one of based on this one.
The next slide. Can you go to the next slide? So, oh wait, maybe it was the last slide. Okay, no, it is the slide. So, how are they not just picking a threshold to a different step in the algorithm, right? It's a probability threshold, so maybe it is more interpretable than the ICA threshold, which is like a scale varying like thing at the end. But I don't know. This seems to me like a cop out. If I understand.
Based on 0.5 is only one sentence. A common choice of 0.5, which has been widely adopted as a marginal median posterior inclusion probability. 32. For model selection in linear regression and cite Barbary and Berg further 2004.
I get the argument that this is like a common threshold and it's a probability threshold, so directly interpretable as well, versus the ICA threshold is like kind of hard to determine and interpret. Okay. Well, less annoying, but
No, the dense papers, right? There's hard to write and not having any mistakes and stuff. Just
they do have a big typo in one of their figures, which I thought was very funny.
and it is statistical association journal, so it's
sense. Okay. So I just gave a quick explain of the Gaussian precise. I think I should put it earlier. So a Gaussian precise is a probability model over functions. It defines a distribution over possible functions at a fixed set of points, assuming that any finite collection of function values has a joint Gaussian distribution. So I don't know if I can explain it easier. So I was also just understand the Gaussian precise from this paper. So from my understanding is the function is sampled from like if you define a continuous function, so this function is sampled from infinite dimension function space, which has a mean and covariance kernel. So the Gaussian precise is sample the functions from it. So basically, the Gaussian precise you can just consider as in the basis, consider as the prior. We just give a distribution of the functions, so which follows a Gaussian distribution. This is what the Gaussian precise is trying to do here. And chi is a covariance function of the kernel. So for their posterior computation, because this is trying to, I just include how they solve the most difficult part is because for each of the Sj we consider as a Latin function, which is theoretically it's infinite. Which if you want to sample from a Gaussian precise of it will be very difficult and computation expensive. So what they do is they are trying to do like an eigen decomposition to represent the Latin function simply. Why they can do this? This will back to the sparsity and the smooth assumption of this Latin functions, which makes this decomposition we can select the just top couple of eigenfunctions to represent the Latin functions. So which can make the sampling precise easier and more efficient, and do not, in the meanwhile, do not lose much features. Yeah, this I just explained as far as we'll keep the first L eigenfunctions after the eigen decomposition of the doesn't size. So because if we represent Gaussian precise as a eigen, like the first L eigen combination, so the final Sj Latin functions can also be considered as the linear combination of the psi c. Can be considered as the linear combination of the psi c, because psi is the eigenfunctions, at least of orthogonal eigenfunctions. So it can be represented as a linear combination of them. And then this precise is to the thresholding part. This is what they use the thresholded Gaussian precise. So to sampling this Latin functions. Okay. My explanation may be confused. Let me know if you don't understand anything.
Maybe it will help to explain what exactly do they run the eigen decomposition on, right? Or are they just estimating the eigen decomposition directly?
I think yes.
That's what they're doing. Is estimating it directly.
Yeah. So it's you have a rotation function. You have an orthogonal basis that you're searching for. Yeah. They like rotations. They started with one meniscus, and then this also. It's like, okay, well, we'll only work with rotations.
Okay. I hope I didn't confuse people about this. Well, for their sampling precise, actually, I didn't go through how they updating the algorithm that part. I haven't read to that part. It's all their supplementary part. But for all of the mixing matrix and the noise part, they're using just basically of sampling because they have fixed have their prior form can be used directly with the CMC sampling process. And I just didn't go through. I just list all of them how to sample this precise. So if actually you're interested, you can read all their supplementary material there, 40 pages of math. It's just I cannot read all of them. This is how they sample it. So actually, all of this is a method. I think because of all their sampling process, and so with one the stochastic gradient, the Hamilton motor colors the design particular for because their function is not after thresholding is not a continuous function anymore. So it's for traditional sampling is not suitable for that. So this is why they introduced a stochastic gradient motor color there. And I think it's the all mathematical updating part you can read yourselves better understand than I explain. And actually, I don't understand. And that's all is the algorithm. I think if you have any questions of I just give like structure of how this sampling is doing. If you have any question of why there's structures, you can ask me now. So
there's lots of choices that they make that are not really explained, like why the prior they choose is used.
Oh, they explain. Yes.
It's like a neural network.
No.
No, really, Bayesian modeling is like a neural network. You create your posterior by random choices, sort of, just
Yes.
five of it, and then they tack it on, like, okay, this prior will look like that, will look like that. Okay, we got this gigantic. How do we train it? MCMC. That's in our case, SGD.
Yeah,
and
I read this paper trying to understand this process. You just summarize in like a few sentences.
No, like 20 years on that. Trying and
yes. Basically, we all know that posterior proportional to likelihood to prior, and what is it?
No, I mean it doesn't matter. Yeah, like when you realize, oh, it doesn't really matter. It's just a engineering tool. Like you build it and you see it works. Okay, you see it doesn't work. Let's change it and see it like that.
Yeah, let's talk about the results.
Yeah.
The result looks.
And MCMC is slow, right? It used to be slow. So I don't know. I've heard that.
If you remember, I just told Brad about their initialization. It's using Infomax result.
Oh, they start from Infomax.
Yes.
Oh, I see.
That makes it much easier. So, but I don't know.
It's like a sharpening algorithm for Infomax. Post tuning.
I also posing so
you don't have to pick a threshold, and then you have to run MCFC of your results. So, yeah, it's weird. And they're like, yeah, I don't know.
Oh, so do you have to run high rank Infomax then? Because
probably,
I don't know. If you run 53 components, you will never get initialize. You will never get 70 components, right? Even though you're flexible with components.
Or they just run it on a full image.
Yeah. Doesn't they just measure Infomax one time for the initialization? I was looking for why they use it. Just didn't explain.
Yeah, it's weird. It's intriguing. So I'm always like looking for Infomax alternatives and stuff, but then like all the alternatives either just use Infomax or are like not really fair.
I mean, maybe I missed something.
Yaorong method doesn't use Infomax.
That's why I was 73.
Yeah, this is why I'm interested in the result until I say their initialization.
4,000 iterations with okay, so 6,000 iterations.
I don't remember which scenario we used. Probably all of them. They kind of like 1, 2, 3, 4 experiments. For first two is like one is sharper edges. Another one has blurred, more smooth edges, and the results like this very good. It's much better than Informax on this smooth edge. It's also good on the sharp edges. Like just Informax with this can be a result. So this is a result of their.
Yeah. Okay, now we know what we're looking at.
Yeah, so
what ICA is Informax, right?
Yeah, Informax. They just compare with the Informax with or without threshold. And the PIV map is the probability of accepted or not. Just a cable of the point there. This is just a point represent
What's
the probability.
Oh, single round 100 rounds. Okay.
Yeah.
Average over 100 rounds.
What?
Average over 100
Yes.
rounds. Informax gets confused if you have, well, of course, you're averaging. So. Well, I don't know. This falls into Rogers' realm on this Dovich's paper with a square, all that stuff. Are they? I wonder if they're making sure the joint distribution is correct, etc. Okay.
And there's for the smooth result, smooth component. It's for me, it's kind of studying of how they get this.
Well, they're getting like a blob still. They're not getting the triangle. I can in the ground truth I can see the triangle.
They assume independence. But I do not see it.
But the sources are not independent. Are they making the sources independent? That's the thing. That's what like, Rogers wrote papers about that. It's for simulation. So the sources may not be independent. If they didn't take care because they overlap, etc., etc., they're not statistically independent, likely.
I didn't look.
And they enforce the independent. Okay.
Yeah, this is another thing I was weird about this paper, and you talked a little bit about it. They say like one of the limitations of ICA that they had just for this paper is that their method explicitly models spatial dependence of length of signals. And I kind of get what they're saying here. They're saying like, okay, yeah, things in the brain are spatially similar, in some way, but I don't entirely buy like what they're saying and like how this is like is really a like blind first separation with what we do with spatial MDA. Like it seems like they're doing something almost different. Like they're not assuming spatial independence, really. They're kind of assuming spatial dependence, but somehow I don't know. They're not doing temporal ICA, so I'm not really clear what they're like what's happening in terms of the independence of the sources even.
Yeah, I remember it just.
I'm just looking at the introduction where they say that their method models spatial independence of the late source signals. What that means for sources that should be independent if you're doing spatial ICA, I don't know what that means.
They tried it on fMRI data, right? Okay.
Yeah. I get it.
No, but Informax has like strict assumptions about independence of the sources and types of sources.
Right.
And spatial. Yeah. Maybe Rogers could present his paper on how those assumptions translate into the simulations and things like that.
Yeah.
And one thing is apparently their mixing measure has a lower average distance for all of the results compared with the Informax. And especially for like the smooth edge one, it's very sensitive. I think sensitive to noise. Yeah, it's a low, medium, high noise level. So it's less sensitive to the noise. So
no, Informax is flat, right? If you look at the scenario 2, Informax performance doesn't change much if you look at the median with noise, and their performance linearly suffers.
Which means
If you
better or not. I know what you're talking about.
Yeah, like look at this. This median is good at low noise, worse at medium noise, and even worse for Infomax. I mean, it doesn't matter. The noise doesn't affect it. I mean, it's worse from the start, but it's robust. It's just it doesn't.
Yeah, I saw this.
In the same for scenario one as well, but for them it's different than scenario one. So noise is orthogonal dimension feels like they start doing better with noise in scenario one.
So noise I remember.
Can I add something here?
Yeah,
Just that the threshold for separation that I typically use is an MRE error of 0.1. And it looks like on the scenario 2 that everything is above that. So nothing is really being separated from that perspective. Everything is failing.
Yeah, but you can see that. But the sources are not independent. They didn't do, I bet they didn't do what you do in simulations.
I didn't get if they assumed independence in their model. Are they optimized?
No, they do. Oh, maybe they assume just.
Could you repeat, please?
Oh, go ahead.
Oh no, I'm just trying to where is mentioning independence. Oh, this is independent. The assumption is not necessarily required for establishing the subtopic properties of their model. But it's generally assumed the implicit separation of neural image and leads to more efficient posterior computation of this.
Okay, so no?
No, they assume that, but they didn't explain why.
They assume independent.
Yes. No, yes, they assume, and they mentioned about that is because most of blind spot separation assume that, so they assume.
But they don't enforce it in their algorithm. Like the algorithm doesn't require it.
No,
or does it?
It doesn't. In the assumptions, never assume all of their inference commutation, no independence mentioned.
So the model does not favor independence.
Or of course. But then why didn't they get those sources? Because of the overlap. If you look at the triangles.
So my point about the simulation is, just to wrap it up, is if they did embed independence as a thing that they want to recover, independence is something that they want to recover from the data, and it's built into the model, then they should have simulated that way. If they didn't, as long as they simulated the data the way that the model was designed, like in agreement with their model, it should be fine if it's not independent. Really. Does that make sense?
Yeah, kind of. But I have a problem with their assumption of non-overlapping components. Even in their simulation, they're overlapping. And in the brain, I assume some neurons would engage in different activity, like a functional activity.
Yeah, I noticed they had a reference to an old paper from Smith. Yeah, that didn't strike me the right way.
Yeah.
It was kind of like strange. I didn't get that from that paper.
Oh, you looked at Steve Smith's paper?
Long time ago. I think that's the one about PCA. Yeah.
Yeah. I'm not sure. It's just too strong of a assumption of non-overlapping regions in the brain. I mean, somewhere maybe, but even in their simulations, they're overlapping. And most interesting part, they're going to this
Well, actually, for my understanding, even if they assume non-overlapping part, but I do not see it matters on their inference part when they're computing the for each latent functions fj is for one specific location. For sjsi, if they both active, I think it's fine based on their inference. But they assume non-overlap with I forget, or maybe it doesn't mention why they assume non-overlap. So I think it's fine for their result. I just do not see any strong strict of this overlapping property. Yeah, they see that they typically they assume there's no overlapping, but in their simulation start they consider case one. Okay. No, they just give what they did. And anyway, I think that's the result of it. We continue our study. Sure, and they also give another experiment on the same TV. So, which is the image size 100 to 100. There are 5 templates from the same TV, and there are total 100 time points, and noise added, and total 100 simulated subjects. So the results of this one are just basically the result pictures here. So looks good before.
Yeah, that's probably what you mean, Brad. That is also good here on SimTV.
Yeah. So, but if they start from Informax, this is all I'm kind of curious. I don't know if this one they still start from Informax. So just mention it how they run MCMC and say, okay, we initialize run Informax first, that kind of initialization. And for each experiment, it just doesn't mention about that. I don't know if they use it or not.
Well, probably they do.
Yeah, I think it should be. And there's the same deep result.
Yeah, but the results are not that good. If you look at the true latent sources and look at the posteriors, the yellow, the posteriors tend to be the mode collapse ones. They're not smooth. They're again binarizing, tend to binarize, even though they're trying to do distribution. Look at the top one; it's smooth and falling off from the center, tapering off, like disappearing. And if you look at probabilities in yellow, they're just binary. I mean, they're not fully binary, but it's not smooth. But yeah, I keep hearing about segmentation and things like that. Doing the semantic segmentation binary or categorical is not that useful as if you're doing probabilities, because everyone knows voxels are just random cut, etc., etc., etc. So the tapering off, and we've tried actually in our models to look at logits, like or after softmax, and they still tend to be like that binary. They're not smoothly modeling the probability, even though it is a logistic function. That's interesting. Okay, go ahead. Yeah, we should start wrapping up.
Another thing is on the real data. So
okay.
Okay, got this one. So the result is from Informax and MPSV. They have like a couple of metrics to develop that I just didn't look at. I just look at it. They have better than that with already known brain networks. So and it's a better results. It's just it. So I think just the paper result image figures here. And for their future work, they want to extend to multimodal modality brain images or the spatial temporal models. So that's all.
Yeah.
And my main
Did they run Informax on the real data too?
Yeah, that's the
top is Informax their result.
So what's the comment about no whitening needed?
Just it's a button to whitening. Because it's only single subject, if I remember. It's one subject for on all of subjects.
But if they start from Informax already done the white. So that works.
Exactly, that's what I mean.
There should not be here. I forget. Just lost the slides. Missed something.
Is that a point that they make explicitly? Like, hey, that's a benefit. We don't do whitening.
What, Roger?
Do they claim they don't do white?
Oh, if I remember, yes. I cannot include here. They have too much things.
Do we have team up talk right now at one?
BSS today.
Yeah, but we need to wrap up. It's time. And thanks, Yaorong. That's good. That's very interesting.
Thank you.
Does anyone else have questions? It's always three usual suspects discussing stuff. Well, sometimes two usual suspects. And Rogers, thanks for joining.
Probably it doesn't matter what name.
No, they don't. It's probably
maybe I don't know why I'm going here.
wishful thinking. Yaorong wants to get rid of whitening. Yeah. Thanks everyone, and thank you.